All right, we're going to continue with the other three items on this problem. We're going to find the intervals where f is concave up and concave down. We're going to find the hypercritical points, and we're going to say whether the hypercritical points are inflection points. Okay, so this is where we left off. We had found intervals where f was increasing and decreasing. We had found a local maximum and a local minimum, and we had found points and intervals and wrote them all out. Now, let's continue. So first thing is we're going to be doing second derivative information now. So we need to pick up where we left off with the derivatives. I'm just leaving myself a little note here. We need to take the derivative again. Okay, if you haven't done this yet, pause the video, work out the derivative, and then come back and check. Okay, f double prime should be negative 9 times 2x plus 8. By now, you may be able to do the derivative and the cleanup in your head all at once. The final result is that f double prime of x is negative 18x plus 8. Next, we should find hypercritical numbers. Do you remember how to do that? To find hypercritical numbers, we'll set f double prime equal to 0 and solve. So negative 18x plus 8 equals 0. This is a linear equation. It should be easy to solve. Just be careful that you don't make a sign mistake as you move numbers around. Since x comes out to be negative 8 over negative 18, we can do a double negative simplification, and that will leave us with x equals 4/9. This number, incidentally, is exactly halfway between the two critical numbers. That's something that is typical of cubic functions. Other functions may not have that property. So here we go. There is one hypercritical number so I'll just name it B1 4/9. So as before, I'll draw a number line so that we can keep track of the information that we figured out. And as before, I'm going to use my grid so that every dot on the grid is worth a tenth. And I'm going to use the same number line exactly that I used before, so that if you wanted to, you could put the two number lines together. So there's x. 4/9, by the way, is 0.4 repeating, which puts it right about here. So there's B1. That means that the domain, which in this case is the entire real line, is cut into two intervals. One of them is over here, and the other one's over there. As before, I'll set up a table just to keep myself organized. This time, I'm going to do a table of values of f double prime. I'll alternate between test and hypercritical numbers. So it's going to be a short table. There's only one hypercritical number. In this first interval on the left, I can pick any number to test. 0's nice and easy. I'll do that. In the second interval there on the right, I can pick any number I'll use 1 again. So there's f double prime. I'm going to type that into the calculator as y3. So let me go to the y equals screen. I'm going to turn off y1 and I'll turn off y2 and go down to y3 and type in f double prime, which is negative 18x plus 8. Now when I go to the table, you can see that my x values from previous calculations are still there. And as a matter of fact, the 0 that I wanted to test is already there. This says that f double prime of 0 is 8. This is C1. We don't really need that. This is the other number I wanted to test. Just to be safe, I'm going to go here because the hypercritical number is 0.44. That should go in between these two rows of the table. I'm going to go here and do second and this button that says insert, and that puts in a row, and I can now type in 4/9 for x, and you can see that indeed f double prime of 4/9 is 0. So that's good. All right, so this number, and then this number are the ones that I want to transfer. If you want, you can delete the other rows. I'm going to leave them in, and you'll see why in a minute. So we determined that f double prime of 0 was 8, f double prime of 4/9 is 0, and f double prime of 1 is negative 10. This tells me that in the first interval, f double prime is positive. This tells me that in the second interval, f double prime is negative. And just to be complete, f double prime is 0 right there at the hypercritical number. So again, these are the numbers I'm reading to get the signs in the intervals determined by those test numbers. That's information about f double prime. To get information about f, remember that a function is concave up where f double prime is positive and concave down where f double prime is negative. You got to watch this because this is not increasing decreasing information because we are looking at f double prime this time. In this first interval, f double prime is positive, so f is concave up. In the second interval, f double prime is negative, so f is concave down. There's a hypercritical point here at B1, and since f is concave up on one side and concave down on the other side, it switches concavity, which means that this is an inflection point. So I'm going to draw a little swerve there to remind myself that this is an inflection point. Okay, so let's write out all of this. F is, this is again information about the first interval, and we determined that f is concave up. So f is concave up on the interval. All right, now what interval do I write? The interval starts, well, it goes all the way to the left, and then it goes all the way past the test numbers to B1. So I should write, well, all the way to the left, that means negative infinity, and then up to the test number, that's 4/9. Sorry, up to the critical number, that's 4/9. Past the test number, up to the critical number, hypercritical number. For the second interval, let me see if I can state it correctly this time the first time. We determined that f is concave down. The interval starts at the hypercritical number and goes all the way to the right. So f is concave down on the interval. It starts at the hypercritical number 4/9 and it goes all the way to the right to infinity. So as before, each interval picks up where the previous interval left off, assuming that you've listed everything in order from least to greatest. And again, the hypercritical number is used as the boundary of the interval to the left and right. Then we've got this inflection point. Let's write that down. F has an inflection point at, well, what is the x-coordinate of the inflection point? It's the hypercritical number. That's 4/9. What about the y-coordinate? What is the y-coordinate of this point? Again, none of the numbers in this table are the y-coordinate that we need. Instead, remember, this is a point on the graph of f. So to get the y-coordinate, plug the x-coordinate into the original function f. Okay, let's go back to the calculator. I'm going to go back to the y equals screen, and I'm going to turn on y1. I'm going to leave y2 turned off. That's f prime, remember. And then for y3, I'm going to turn it off because we really don't need it anymore. And now when I go to the table, I have x coordinates and y1 is a column of f of x values. The x coordinate that I'm interested in is this 4/9 that I typed in earlier, and there is f of 4/9. So that's 2.0823, and we'll stop there. So here we go. 2.0823. Now that we've got all the information, let's sketch the graph. First, let's just be sure that we agree on the x-coordinates, the x range, and the y range. If you look back at the number lines, it looks like going from 0 to 1 is a pretty good range. That'll give us a little bit of space to the left and right of the two critical points. The hypercritical point is there in the middle. So we'll set our x range to be from 0 to 1. The y range is going to be a little bit of a challenge because if you look at the two critical points, the local maximum and the local minimum, these 2 points are at their y coordinates are rather close together. So I'm going to show you a convention that you'll sometimes see for drawing just part of the y-axis without going all the way down to 0. This is, you got to be careful doing this, but it is useful, and we should have the y range go from, say, I don't know, 1.8 to maybe 2.4. Okay, so the x-axis will be pretty easy to draw. The y-axis, I'm going to draw this much of it, and then I'm going to draw a zigzag. That's one of the conventions that's used to indicate that I'm not going to include that part of the axis. And the reason for that is that now I can do 1.8, 2.0, 2.2, 2.4. So I have skipped all of the space between 0 and 1.8. And again, the reason for that is that if I put it in, the graph would be very, very tall and not very wide, and it would just be hard to look at. So there you go. Now, we've got numbers displayed on the calculator now. All of these are points on the graph of f. We want to be sure to show this one, that 0.15, remember, is the critical number associated with the local minimum. This is the second critical number, that's the local maximum. This is the inflection point, that's 4/9. The 0, the 0.5, and the 1 are just other values of x that we used as test numbers. But since the calculator is showing us y values, we may as well plot some dots. So I'm going to plot these dots on the axes. Okay, so first, let me change colors again. So there's a point at 0, 2. That's right there. The next one is at 0.15, 1.93 or so. So 0.15 is about here, and then we're going to do 1.93, so that's going to be about there. And that, remember, is the local minimum. So I'm going to draw a little bit of a minimum there to remind me of what that's supposed to be. The next number in my table, well, that's x equals 4/9. That's going to be the inflection point. So that's 2.08. That's close to 2.1. So here we go. There's about 0.44, and 2.0, 2.08 is going to be right about there. And remember, this is an inflection point where the graph swerves from concave up to concave down. So I will draw a little bit of a swerve here just to remind myself of what's supposed to happen there. This next number, the 0.5 was just a test number. So this is just going to give us a dot at 0.5, 2.125. So 0.5 is this column, and then 2.125 is going to be a little bit above there. So yeah, not too far from our other dot. This dot, this point is the local maximum. So 0.738, 2.23. Okay, 0.7 is here, 0.738 is over there, and I have to go up to 2.23. So I'll go up, there's 2.2, 2.23, so somewhere around there. And that's a local maximum, so I'll draw a little bit of a maximum to remind myself of that. And finally, if you take x equals 1, y is equal to 2. So 1, y is equal to 2. The 3 points that you really need to show are the maximum, the minimum, and the inflection point. If you want, you can leave the others out. Like I said, I'm just putting them in because they're in the calculator anyway, and they give me more dots to connect. Now, as to checking that this is all consistent, first, when we did the f prime chart, the arrows, as you can see, are giving us a shape like that. That is completely consistent with the shape that we're getting here. furthermore, the critical number C1 is at about 0.15, so that's about here. Notice that f is concave up at C1. That means that from the second derivative test, there must be what? A local minimum at C1. It's at the bottom of a valley. That means that the first derivative test and the second derivative test agree about what kind of critical point C1 is. C2 was 0.73, so that's over here somewhere. That occurs where f is concave down, so the second derivative test agrees that there should be a local maximum at C2. So all of the information from the first derivative and the second derivative, all of that information is consistent. It's also consistent with the heights of points, because remember, what's supposed to happen is something like that. So the function decreases and is concave up. It hits the bottom of the valley. It continues to be concave up until we get to that inflection point. Now it switches to being concave down, but it's still going uphill aiming for this local maximum. So concave down, we're now going up a hill. We went up out of a valley here. We're going to go up the hill there. Then we go over the top of the hill and we're now going down the hill. There's our graph. Just to check it with the calculator, I'm going to set the plot window to look as much as possible like the graph that I just drew. So I'll set x-min to be 0 and the y-min to be 1. And I'll use 0.1 for the x scale. Remember, that's how often it will draw tick marks. For y-min, I'm going to use 1.8. For y-max, I'll use 2.4. And if you look back at how I used the grid here, the vertical spacing is also tenths. So I'll make this 0.1. Now with any luck, when I hit the graph button, I should get something that looks just like what we drew. And there you go. So again, to summarize, we started by doing all of the f prime information. That's critical numbers, and then test numbers to tell us where f is increasing and decreasing. In the process of doing that, I usually put I drew that in the wrong place. I usually put f in as y1 and f prime in as y2, and use the table feature to quickly plug in these x values to get these values out of the y2 column. But then these values come out of the y1 column. Those are values of f. Those are y coordinates. Then we found f double prime. We solved for the hypercritical number. And again, I put f double prime in as y3. So this column of numbers comes from y3, but then this number is a y coordinate of a point on the graph, so that comes from y1. That's a value of f. And then finally, I sketched the graph with all of my points visible and confirmed with the calculator that it was correct. Some things that I will be looking for when I'm grading is that I do want to see the intervals written out. That's intervals where f is increasing and decreasing, and you need to tell me also that f is increasing on one interval, decreasing on another interval, concave up on an interval, concave down on an interval. If you want to list the increasing intervals together, that's fine as well. I wrote it out like this just to show you how to read the table and get that information. I'm also looking for local maximum and local minimum points and inflection points, and I need to see both coordinates. When you draw the graph, be sure to use a reasonable scale. Be sure to use a consistent scale as well. If you need to leave out part of the axis, then that's okay. Just leave some indication that you've left out part of the axis. And with that, I will end this demonstration and ask you to send me any questions you might have.